So next topic is semi-empirical mass formula. So the semi-empirical mass formula, which is also known as Bethe-Weizsäcker mass formula, it gives an expression for binding energy which is based on the liquid drop model theory of nucleus. So in this case we will find an expression for the binding energy considering that the nucleus act like a drop of liquid. So the formula is the following: EB equals to AVA, where A is the mass number, minus AS into A to the power 2 by 3 minus AC into Z minus 1 divided by A to the power 1 by 3, where Z is the proton number or atomic number, minus A asymmetric. Okay, it will be asymmetric, so we are writing only asym this part, into A minus 2Z whole square divided by A, then plus minus delta 0 AP divided by A to the power KP, where A is mass number of the nucleus, Z is the atomic number of the nucleus, KP, this KP here is half according to, so sometimes you will find that here instead of A to the power Kp, in different books you will find that they have written A to the power half sometimes, or in some other books they have written A to the power 3 by 4. So both the values are valid. This A to the power half, this is according to the modern experimental nuclear data, and if you find that there is A to the power 3 by 4, then this 3 by 4 is according to old experimental data. Okay, where this AVA, this term is called Coulomb volume energy term. This second term is called the surface energy term, that's why we have AS. The third term is the Coulomb energy term, so that's why we have this AC. Then this fourth term is the asymmetric term, so we have this A asymmetric, and this fifth term is called pairing energy term, so we have this AP. So where this delta 0 is plus 1 for even proton and even neutron and even proton. So if in a nucleus there is even number of proton and even number of neutron, then delta 0 is plus. For example, helium. Okay, so for example is helium, where neutron number is 2, proton number is also 2, this kind of thing, then delta 0 is plus 1. And then delta 0 is 0 for even neutron or odd and even pair of neutron and proton. Means neutron may be odd number, proton may be even number, or neutron may be even number, proton may be odd number. One example can be this one. If you consider this nuclide of lithium 37, then here proton number is 3, which is odd, and neutron number is 4, which is even. So for such kind of nuclide, delta 0 is 0. Another example of this case is this one. Think about this one, C6 13. Here proton number is even 6, but neutron number is odd 7. So these two cases, for these two cases where either neutron is odd, proton is even, or proton is odd, neutron is even, in this case delta 0 is 0. And for odd nuclei, odd number of neutron and proton, where both the neutron number and proton number are odd, then delta 0 is minus 1. One example can be this one, another nuclide of lithium 36, okay, where proton number is 3 odd and neutron number is also 3 odd. For such kind of nuclide where both proton and neutron number are odd, delta 0 is minus 1.